Now, okay, you first.
No.
After.
All right.
Okay, I'll go first. Now we're going to look at molecule polarity, which is very, very similar to bond polarity. You're looking at electronegativity values, except now in a molecule, you are considering more than one bond. It's not just two atoms bonded together. There are multiple bonds that have a net effect on the total molecule.
Unless, of course, it's linear.
Unless, of course, it's linear, then it's the same darn thing you did in the last podcast.
Right.
H and H, is that going to be polar or nonpolar?
I'm going to say nonpolar.
Nonpolar. It's a tug of war. They are both the same electronegativity. Pulling on those two electrons the same. Nonpolar. H and F.
Polar.
Polar. Fluorine pulls the electrons. You can kind of see,
this
is like a little density graph. You can see fluorine is going to have that electron more than hydrogen. It's going to be polar. The electrons are negative, partially negative. Hydrogen loses it, partially positive. A linear molecule is the exact same as a polar bond. You have two things to consider.
Yep, only one bond to talk about.
But now it's going to get a little dicey. Talking about a bent molecule, let's consider three atoms.
Three atoms, and bent molecules have how many bonds? They have two bonds.
Two bonds, because one of them's in the middle.
So we're going to have to talk about the bonds' relation to each other.
Here's water. And let's draw the Lewis structure. And 2 dimensions are going to help us here. All right. Now, by itself, the OH bond is polar. Looks good.
Nice.
But I have 2 OH bonds. Okay? It is bent. It's very important you draw your Lewis diagram at the 90-degree angle here. It's bent.
Yeah, you don't want to draw them straight across because that gives you a very false perception of what this molecule looks like.
Okay? So let's look at the central atom. Focus on the central atom. Focal. We'll just cross that out. Focus on the center atom. In this case, the oxygen. What's happening? It has electrons around it here and here. Okay, so it has a lot of electrons.
Yeah.
What's happening in each one of these bonds, though?
There's also some electrons.
There's electrons in the bonds, and because of the electronegativity values, oxygen is pulling those towards it.
Yep.
Because oxygen is more electronegative than hydrogen. Okay?
So it looks like, to me, all of the electrons are being pulled to one point in this molecule.
The oxygen.
Yeah.
So oxygen is actually very polar because they're both going this direction. The net effect is, if I were to just kind of draw a line down this center of this molecule, and this is a very visual thing. You're looking for how symmetrical it is. All the electrons are being pulled past that line. This side of the molecule is going to be very negative.
Well, that must mean that the hydrogen side of the molecule is going to be positive.
Positive.
Because the electrons are being pulled away.
And you're just looking at the symmetry and where the electrons are going to see if it's positive or negative, or if it's polar at all. Next, we will consider
a 4-atom molecule.
This one's trigonal pyramidal.
Okay, so our 4-atom molecule, the trigonal pyramidal molecule, I got to say that right. Where this starts to get difficult is you're going to have to start taking the pictures we draw on paper and kind of imagining what they look like in 3 dimension. We've got a picture here of what the ammonia molecule looks like in 3 dimensions, and you get a lone pair up on top, at the peak of the pyramid, and then there's 3 hydrogens down at the bottom. So we need to consider what the nitrogen-hydrogen bond's polarity is in the first place, and it's clearly
polar. The nitrogen actually pulls the electrons. It's more electronegative because it's closer to the top right. That's negative. The hydrogen's positive.
So if we look at that picture of the pyramid, all those bonds then, the electrons are being pulled up to the peak of the pyramid towards the nitrogen, and we already have a pair of electrons up there. So if you consider the symmetry again, like we did with the water.
If we kind of drew a line here across the 3-dimensional model, all the electrons are going this way, up towards the top. That means the top will be a little bit negative near the nitrogen, and the hydrogens on the bottom will be a little bit positive.
And you can see from the paper and pencil drawing that you still have some asymmetry in this drawing. If your drawing is perfectly symmetrical, that makes it really hard to determine if it's polar or not. But if an asymmetrical drawing like this, it can be pretty obvious to see that if the drawing's not symmetrical, then there must be some polarity in the overall molecule.
So if it's not symmetrical, asymmetrical, those mean the same thing, you have some polarity. Okay, this one is probably not as polar as the water because the water had a lot more. It was a lot more asymmetrical. And here we have the 5-atom molecule, the tetrahedron CH4. And let's consider again, they're all carbon-hydrogen bonds. What happens?
Well, we pretty much have the same tetrahedral electron pair arrangement that we had with all the other ones, but now we actually have a tetrahedral shape too. So when we consider the carbon-hydrogen bond, we know that the carbon-hydrogen bond is, again, polar. Carbon is more electronegative than hydrogen, so it pulls the electrons towards it, giving the carbon a slightly negative charge.
However, since the hydrogens are the same on all 4 sides, all the electrons are being pulled inside the atom evenly.
So this is a really symmetrical molecule.
Very symmetrical, which means what?
That there's symmetry?
It means there's symmetry, and it is non-polar.
So if you get that symmetry and all of the electrons are being pulled equally, basically, you get a nonpolar molecule.
It's non-polar.
This does take a little bit of imagination, though, so exercise yours.
Sometimes it helps to look at these in Lewis structures, even though it's not the exact same, but you can see in 2 dimensions how this is very symmetrical. It's a decent representation of what's happening in 3 dimensions.
So unlike the ammonium ion or atom that we just took a look at, that was unsymmetrical on paper. This is nice and symmetrical on paper, so you can kind of see how the polar bonds are going to cancel each other out, essentially. We're going to try some examples here to describe these molecules as being polar or nonpolar. And this is where it gets a little bit more tricky because all the ones we've been considering so far have really just been made up of 2 different atoms. We've got a couple here made up of 3 different types of elements, I should say.
So let's look at the first one. We already did CH4. Now let's do CCl4. Tetrahedral, because there's 4 bonds. The CCl bond is now polar the other way. Chlorine is more electronegative than carbon, so that's negative, and the carbon is positive. So all of these are being pulled out.
And so we consider the symmetry again, and this is a very nice and symmetrical molecule. So the electrons may be being pulled out toward the chlorines, but that makes it nonpolar because they're all being pulled out equally towards each different chlorine.
In all 4 directions. So nonpolar CCl4. All right. Let's go down here to, let's replace one of those chlorines with a hydrogen.
So from the previous example, we know already the carbon-chlorine bond is polar and it's pulling the electrons towards the chlorines. And from our example on the previous slide, we also know the carbon-hydrogen bond is polar, but in this case, the electrons are pulled towards the carbon.
So what happens then? You've got, remember this is 3-dimensional, but the carbons are pulling down on the bottom, down and towards the outside, but the hydrogen's pulling towards the middle. So there's a little bit of asymmetry here.
Yeah, so you get the electrons being pulled basically in one direction versus another.
And on the bottom side, it's negative because that's where all the electrons are being pulled, in that direction. And the top is going to be a little positive because they're being pulled away from that. We can do the same exact thing with CH3Cl.
So now instead of having 3 Cls, we're switching it up. We've got 3 hydrogens and only 1 Cl. Again, this is a very non-symmetrical molecule, just like the last one we considered.
The electrons for the hydrogens are being pulled in toward the carbon, but then the carbon and the chlorine are fighting the other way. Chlorine beats the carbon. There's more asymmetry. All the electrons are being towards the center and then up to the chlorine in that general direction. So the chlorine side is going to be negative. All 3 hydrogens are going to be positive.
All right, so now the last one we have here, there's an equal number of chlorine and hydrogens bonded to that central carbon atom. So you got 2 chlorines and 2 hydrogens.
And this is 3-dimensional, so I'm going to draw them 90 degrees apart rather than
across from
each other, because that would be a little deceiving. Because remember, this is all tetrahedral. But this shows it a little better. What's happening? Carbon pulls towards the center for the hydrogens, but the chlorines pull away from the center, away from the carbon. So you can look at the arrows, kind of where's the direction, where are the electrons going?
So it looks like they're being pulled towards the chlorine side of the molecule. So you put that line of symmetry at an angle in the middle of that molecule. Remember, it's 3 dimensions, so basically carbon you have to imagine as a sphere, so you can put that line of symmetry anywhere.
So the chlorine side of the molecule is a little bit negative, the hydrogen side is a little positive. All the electrons are kind of getting pulled in this direction.